All right, let's get into it. Today we're going to be working with combinational logic gate, the resistor switch model for the transistor, perform an analysis on that. We're going to take a look at the power consumption in a logic gate. We're going to look at parasitic capacitance. So we're going to draw out our circuit and then we're going to take it from there. Everything will start to make sense as we flow. All right, so we about to get in that flow state. So we're gonna have this shared supply. This is gonna be where our supply voltage comes from. What we're gonna call a pull-up resistor right here. This is gonna be in series with the MOSFET transistor, straight to ground, which we're step a little further in depth into the transistor. We're gonna look at it because you can see that it's a 3-terminal component. Consider that the supply, and then there's the gate. Okay, so if this were VS in this case, but it's gonna be the voltage drop across the drain and source. This is the drain, yeah, this is the source, and this is the gate. So we have like this, we have a flow of current like this. That's the current through the transistor. We would model it as a voltage controlled current source. The voltage across the drain to source equal the voltage across the gate to source minus the voltage threshold. Which is like, we want a relationship for the current, we would just have ID equals, this is variable K multiplied by this difference, VGS minus VT squared though. So you could also write this as K times VDS squared. Looks much better. That's not really beautiful, ain't gonna lie, but it's looking okay. Alright, we got our inputs A, B. So, the circuit shown below is intended to implement C as a logic function of A and B. Implement C. Oh yeah, okay, so let's have our final output C. This is our reference point. This is what we were looking at. This is what we really want to know about. Let's label our resistors too. How, my bad. How wrong of me to not label my stuff. We're going to take a look at 3 different ways that we could draw this. So let's take a look into how we draw out these like abstractions. We're going to call it a circuit abstraction. I want to actually include this. I want to explain this because it's very important to understand the conversion. Output, this being the input, obviously. This is ground. And this is VS. This is our supply voltage. Equivalent to an inverter. And so this is how you draw an inverter, just like that. Okay. Now that's the logic gate for this combination of components. So I'm going to draw it a little bit smaller. I drew that really big. Alright, it's going to look like this. It's going to be 2 transistors in series with each other. Right, we're always going to include this pull-up resistor. It's just what we do. It's a current limiting resistor. And it's important, okay? So pull-up resistor is what we call it, though. VS. Alright, this with the N in front. This, therefore, would be a NAND gate. That's an AND gate. So there's a distinction between this very minute notation, okay? Okay, you gotta look at these distinctions of this drawing. And that determines the function of the logic abstraction. Way of doing it is like this. Alright, and that's C, A, B. Okay, so these are 3 different ways that we can draw this logic diagram. Alright, these are our logic gates. This is the static discipline that we're given. Vs equals 5 volts. The voltage low out equals 1.4 volts. Okay, very well, very well. Yeah, so what is the low level noise margin? Okay. Okay. Our low input, 2.2 minus 1.4. The range under which we can maintain static discipline. We can't operate with outside of the static discipline. If we do this, then any circuit that communicates, that wants to communicate with our circuit, or any other circuit that our circuit wants to communicate, must undergo similar static discipline. 8 volts. Okay, what is high level noise margin? 1.2 volts. Perfect. Okay, how big is the forbidden region? The forbidden region under which we cannot operate. V in high minus V out. No, in low. So 2.8 volts minus 2.2 volts equals 0.6 volts. All right, beautiful. That is our forbidden region. Well, that is like the range of our forbidden region. It's 0.6 volts. Let me just sharpen a little bit. Let me work on bringing the energy here. On equals 5 kilo ohms. Okay, and now to define what R on is, because we've only expressed the pull-up resistor thus far. To explain R on, this is switch resistor model for the transistor. Okay, let's say that again. R, let's say that one more time. This is the switch resistor model for the transistor. Transistor was off, meaning the gate source voltage was not above the threshold voltage defined by the physical properties of the transistor. If it were off, then the switch resistor model for the transistor would look like R on equivalent to a magnitude of resistance within the mega ohms. Okay, mega ohms. All right. So that's meaning it has an incredibly high resistance and barely any current is passing from drain to source. With the transistor activated, meaning the gate source voltage is above the threshold voltage defined by the physical properties of the transistor, then the switch resistor model for the transistor would look like R on equivalent to 5 kilo ohms. Okay, as we have defined, which was given to us by this problem. Okay, so what is the minimum value that our PU can have, our pull-up resistor can have in kilo ohms and still satisfy the static discipline which we defined right here? This resistor we're on, this one would be off. And if this one were off, this one would be on. And if this one's off, this one's off. Or if this one's on, this one's off. At all times, we're only going to have 2 transistors activated. So to determine RPU, the pull-up resistor, the resistance of the pull-up resistor, we therefore need to, that's the minimum, 1.4 volts equals, remember our voltage divider relationship, our input voltage, which is 5 volts, R on plus RPU. Okay, we know what R on is, so this is going to look like this. Oh, 1400 is what it would be. So it's going to look like this. 1400, can you see that? Yeah. 1400 plus 0.28 R on, or RPU equals R on 5. No, yeah, just R on. Minus 1400, 3600, and then that's going to be divided by 0.28. 857. PU equals 12.9 kilo ohms. Now we have R on equals 5 kilo ohms. Let's choose RPU equals 14 kilo ohms. What is the maximum amount of power in milliwatts that is consumed by this circuit for legitimate logic levels applied at A and B? Let's write our knowns. R on equals 5 kilo ohms. Okay, let's write our pull-up resistor. RPU equals 14 kilo ohms. Okay. S, and then as I said before, only 2 transistors will be activated at a time. So we're going to have a circuit that looks like this. RPU, I'll draw it like that. Parallel with RPU plus R on over 19 kilo ohms. And then the inverse of that, 1000, just times 2, and then take the inverse of that, 9500. Okay, so 5 divided by 9500, that gives us that times 5. Oh, 2.63 millivolts. Or milliwatts, 9,500 ohms. Okay, because that's the equivalent resistance. That's what this equals. Okay, that's that. So now we're going to take 5 volts, which is our source voltage, divided by this equivalent resistance volts, and this is going to equal 5.26 e to the negative 4 amps, or we could write this as 0.526 milliamps. Okay, so anyways, 5 volts times 0.526 milliamps equal 2.63 milliwatts. So that'll be the maximum amount of power consumed by this circuit. Given our choices of R on and RPU, assume that the gate to source capacitance, this is our parasitic capacitance, is 50 femtofarads. Okay, let's take a look at this. So our C gate to source, our capacitance from gate to source equals 50 femtofarads, and that is 50 times E, or times 10 to the negative 15 farads. Time constant for an RC circuit is tau equals RC. Okay, input to our other transistor with the gate to source capacitance, and then this would look like that. But we're not connected to that, right? We have an open circuit here. All right, just like that. That's how we would have to model it to define the rising edge time constant, which is our tau, which is RC. Therefore, it's just going to be tau equals, can you see that? Yes, you can. Tau equals RPU multiplied by C gate source. And that equals, let's see, RPU is 14,000 ohms times 50 e to the negative 15, which is 50 femtofarads. That's 7 e to the negative 10. How do we want to define it? In nanoseconds. So that is 0.7 nanoseconds. Right, our time constant is in seconds. You see that ant on my paper right now? What is the falling edge time constant in nanoseconds for the signal at the node labeled X? Okay, that's gonna look like this. This is R on. This is RPU, our pull-up resistor. This is our gate to source capacitance. Now we want the Thevenin equivalent resistance. To model this as a Thevenin equivalent circuit like this, a resistor in series with a capacitor, which gives us our direct relationship to the time constant. So this is going to simplify the circuit into just a series resistor with a capacitor, and that's going to simplify our tau. Okay. This is R on because we shorted our voltage source. So therefore, it's going to be R Thevenin equals our Thevenin parallel with R on, and so that's going to look like this. Let's see. So we have the inverse of that, and then the inverse of the entire thing. So our Thevenin equivalent resistance is 3,684 ohms. The 3,684 multiplied by 50 e to the negative 15, and that is going to be 0.18 nanoseconds. This was doing an analysis of the circuit at a particular node labeled X, as we see right there. So let's look at this, because that's beautiful and all of that is correct right there. So bask in all of that glory, all glory to God and everything. But I really appreciate you guys being here with me. Thank you so much.